Okay, so we are going to do our 4.6 notes, which are dilations. Our goal today will be to define dilations and apply a dilation to figures on the coordinate plane. A dilation is a non-rigid transformation, so this is the first transformation we've talked about that's not an isometry, so this is a non-isometry. It's a transformation that produces an image that is the same shape, but it does change in size. They are going to be shapes that are similar, because in a dilation, and we'll talk about what the word similar means, but in a dilation, the pre-image and the image are similar. And that's why this term comes up. What this means is they are the same shape. And all the angles will be congruent. The only thing that's going to change is the size. So the stretch or enlargement is when the scale factor which is K, is larger than 1. What's going to happen is the image is going to get larger. So this happens when K is greater than 1. A shrink or reduction is when the scale factor is smaller than 1. Or actually not even just smaller than 1, but it has to be between 0 and 1. And what's going to happen when you multiply by numbers between 0 and 1 are things get smaller. Now, it doesn't include 1, because if you multiply by 1, nothing changes. So, if you think about, I'm not going to be able to demonstrate this. Usually I demonstrate like in Word. If you have an image and you were to make it larger by just making it larger vertically, it distorts the image. If you were to just make it larger horizontally, it distorts the image. So think about a picture, and if you were to stretch it vertically, everyone gets really tall and skinny or narrow and skinny. And if you stretch it horizontally, what happens is things get short and wide. And so it distorts the image. This term similar, if you pull it from the corner and you stretch it out that way, it's like if you were to get a picture that was a 4x6 blown up to an 8x10 or something. They're not going to distort the image. Everything's going to look the same. It just becomes larger. That's what that term similar means. And that's what a stretch / enlargement or a shrink reduction means, is you're not going to change what the image is going to look like. It's just going to become larger or smaller. You don't want to distort the image at all. All right, so properties of dilations. By definition, a dilation with center C and scale factor K is a transformation that maps every point P in the plane to a point P prime, so that if P is not on C, then this CP prime is collinear. So there is a term from Unit 1, as I mentioned before. Units 1, 2, and 3 come back over and over and over again throughout this year. So if P is not on C, then obviously CP prime will be a segment, and it's going to be collinear to CP. Okay, so what that means is if this is the center, and let's say P is right here, P prime would come out here, and what would happen is you can connect all three of these with a line because they would be collinear. You could even extend that. So they're collinear, they form a line. Now CP, the distance between C and P prime, okay, so the distance between these points, is equal to K times the distance between C and P. So depending on what that K factor is, will depend on that distance between C and P prime. Or we can also write this if we solved for k, we would divide both sides by CP. So we would have CP prime, the distance there, over CP. So you can take those distances and fill them in, and you can find k that way. If point P is point C, then C and P are the exact same point, meaning that that distance is 0, and when you multiply 0 by anything, the distance will remain 0, so that's also going to be where P prime is. Now, we already mentioned up here, if k is 1, this is larger than 1 or between 0 and 1, but nothing includes 1, because when you multiply by 1, nothing changes. Okay? Things stay the same. So, in this one, when you're looking at these examples, you have to pay attention to which one is the pre-image versus the image. So this is the pre, this is the image, because that's P prime. So you can look at it from here and say, does it get larger or does it get smaller? This was the original, this is your new. So this one gets larger, so we'll call it an enlargement. Okay, now we're going to have to figure out our scale factor. Now remember, you can find k because the distance between C and P prime over CP. So the distance between C and P prime is up here. That distance is 3. Over the distance between C and P is labeled here. That's 2. So I wrote it over here first because a lot of times you have to reduce the fraction. 3/2 is already reduced. There's no number that go into 3 and 2. So your scale factor is 3/2. That's your k value. K is 3/2. Okay, this one here, this is your pre, this is your image. So what happened from the original to the new? This one gets smaller, so it's a reduction. And I don't care if you call it a stretch and a shrink or an enlargement and a reduction, whatever term you want to use, it does not matter to me. So our scale factor here. Now, sometimes you have to be careful, and I wanted to show this too in this one, is you might be given that this is 2 and that this is 1, and they never tell you that this distance is 3. So when you find CP prime, you have to know the segment addition postulate would tell you that if you want to figure out this whole distance from C to P prime, you're adding 2 and 1 together to have 3 over 2. Okay? So it's very important that you understand that if you're given something like this, or if you're given the whole distance, you have to know the difference of what you're actually finding for k. Now, this would be a really good thing to also put on that index card I told you about. That would be like your glossary of cheat sheet, your cheat sheet with all of our rules and stuff on it. K is equal to C P prime over CP, where C is the center of the dilation. Because this is really important that you know how to do this. So again, if this whole thing is 6, or this whole thing is 12, this portion is 6, this portion is also 6. So you might not be given the full portion, you might be given those parts, and you'll have to figure out, okay, well, I'm no longer given P, but that's okay. I know that K is equal to my center, which is O, the center is O, to A prime over O to A. Now, if I can look at this and know this is a reduction, I'm looking for a number between 0 and 1. Over here, since I knew it was an enlargement, I was looking for a number larger than 1. 3/2 is larger than 1. It's 1.5. But we write it 3/2 because that's how we would multiply it. So let's see here. O to A prime is 6 over O to A is 12. 6 over 12 reduces to 1/2. 1/2 does fall between 0 and 1, so that kind of gives me a little bit more reassurance that I'm doing this correctly. If you get 2, but you're saying it's a reduction, then you know that you probably did the reciprocal, or you didn't look at the numbers accurately. All right, let's take a look at the backside. Use the coordinate plane to plot the pre-image points and apply a scale factor of k equals 3 to determine the dilation, or to determine the dilated image coordinates. Plot the dilation. Okay, so let's plot this first. We have A is at -3, -1. B is at -3, 2. C is at 3, 1. and D is at 3, negative 2. And I'm going to connect all these so it looks like it's going to be a parallelogram, which we really don't care what the shape is as long as we draw the original A, B, C, and D. And then what we're going to do is, since this has a scale factor of 3, K is 3, what we do is we multiply everything by 3. We're going to multiply. So this would tell us that our rule is x comma y goes to 3x comma 3y. Now you actually performed a dilation back in section 1. We did not yet call it a dilation, but you have done this before. So we're multiplying everything by 3. So negative 9, negative 3, negative 9, 6, 9, 3, and 9, negative 6. Now, we're going to go ahead and we're going to plot these. So negative 9, negative 3 is here. Here's your A prime. Now, a really good way to make sure that that's in the right spot is its dilation from the origin. So make sure all 3 of those are collinear. Make sure you could connect the origin, A, and A prime all in a point. I'm not going to draw it in, but I just want you to see that. B is at negative 9, 6. So B prime is there. Again, make sure you can connect all 3 of those with a line, and I can, so that looks good. C prime is at 9, 3. So again, could I connect those with a straight edge? Yep, that looks good. 9, negative 6 is D prime. Make sure you could connect them with a straight edge, and you could. So I can connect the origin, D, and D prime all with a straight edge. So this is the dilated image. This was an enlargement. I already knew that because it was larger than 1 for my scale factor. I was multiplying by 3. You multiply by 3, it gets larger. So there's my image. Pre-image to my image. All right, so the next one. Multiplying by 2/3. Now, when you multiply by a fraction, you're multiplying by the top, dividing by the bottom. So you're going to multiply by 2, divide by 3, times 2 divided by 3. So, again, this rule says you go xy goes to 2/3 x, comma, 2/3 y. You're just going to multiply everything by 2/3. Let's actually plot the original, and then we'll go find our new points. So, negative 6, 6, 6, 6, 9, negative 3, and negative 9, negative 3. So this one we have a trapezoid. And I'll go back and label A, B, C, and D as well. So this is A, B, C, and D. Okay, so then what we're going to do is we are multiplying everything by 2/3. So multiply by 2, divide by 3. So for the x, negative 6 times 2 is negative 12, divided by 3 is negative 4. 6 times 2 is 12, divided by 3, 4. 6 times 2 is 12, divided by 3 is 4. Obviously, 6 is going to be the same as 6. 9 times 2 is 18, divided by 3 is 6. Negative 3 times 2 is negative 6. Negative 6 divided by 3 is negative 2. Negative 9 times 2, and you could do this in a calculator, times by 2 and then divide by 3. I don't care. So negative 9 times 2 is negative 18, divided by 3 is negative 6. Negative 3 times 2 is negative 6, divided by 3 is negative 2. So now we're going to go and plot these points. So negative 4, 4 is right here. That's where A prime is supposed to be. Now double check that you could take the origin, take A and A prime, and connect with a straight edge. That looks good from there. 4, 4 for B prime. Make sure you connect those with a straight edge. That looks good. 6, -2 for C prime. Make sure that those would connect with a straight edge. That looks good. And -6, -2. Would those connect? Yes, they would. So that's your D prime. And there we go. We have our image. Since we do not have, not everybody has compasses, I will show you how to do this one, but you will not be required to do this on your own. So, doing something larger than 1 is actually pretty easy, but when we have to cut things down, that's when it gets a little bit trickier. So because this all forms a line, we can create a line or array, and what we're going to do is we're going to measure that first distance, and that would be 1 times. This would be double, and this would be 3 times. So you're just moving the point of the compass up. So this, if this was A, this up here would be A prime. Now, if this point is B, B prime would be on this ray. So, I measure how far that distance is, and then I'm going to copy it. That would be twice the distance. Up here is 3 times the distance. Then for C, that would be B prime. This would be 1 times the distance. This would be twice the distance. This would be 3 times the distance for C prime. And then we would be able to connect the 3 points. And that would be your dilation.